Good morning, students. I hope that all of you are very good and staying very safely in this corona time, in this pandemic time. I hope that you are all safe, and I'm very much happy, very much delighted to meet you like this. Because of some network issues and technical problems, I'm unable to come before you to teach in live. And the morning itself, I tried for live interaction, but due to network issues of some students and myself, it is unable to connect. So anyhow, I'm uploading this video, and now we are going to start the second chapter, that is electrostatic potential. And capacitance, electrostatic potential and capacitance. Okay, first of all, I'll come to electrostatic potential. Okay, what do you mean by here electrostatic potential? Suppose here if you take a point charge plus q, and here we know that this is all surrounded by, yeah, this around this one some electric field will be there, and here I am defining infinite point. First of all, let me teach some basics. Infinite point, here what do you mean by, most of the times we use this word, what do you mean by infinite point? Infinite point is nothing but the first point beyond the electric field, and here this you can see, this is the electric field. Here is the electric field. What I am saying, this is the infinite point means the first point beyond the electric field, and this is up to this one, this is electric, and this is the infinite point. And infinite point is not only, it is a single point here. It is not a specific point, and there are many infinite points are there. And beyond this one, this point, this point, this point, this, and all these are all infinite points. At infinite points, electric field is equal to 0. And we can say the distance from here to this one, this is r is equal to infinity, r tends to infinite distance. That means, don't think that which is not a measurable one, it is a very longest distance, and this is beyond this electric field, and this r is called as the distance, and that is infinite only. Okay, this is about infinite point. And suppose here if we take a test charge, capital Q is a point charge, and the small q is the test charge. As already in the in the first chapter itself, I told you about this test charge. Test charge in the sense, it is having some qualities. The first one, it is the smallest one, smallest charge. The small q is very less than capital Q. That means if you place here q in this electric field, and the strength of electric field created by this q should not be changed. The magnitude or the electric field created by this test charge is very negligible when compared with this one. That is the thing. And second thing is, q is positive. Q is positive. Okay, these are the basic properties of the test charge, and here we have taken a test charge here. First, let me define here potential difference. I'll define first one, potential difference. Potential difference between 2 points. Between 2 points. Okay. So here, suppose if you want to find out potential difference between this point and this point, and let me call this is the point R, and this is the point P. So here you place here a test charge Q, and this is the positive charge, and this is a positive charge. We know that between two like charges there exists a repulsive force. So here this will apply force, electric force, Fe. So here I would like to bring this test charge from R to P. So to bring this test charge from R to P, we need to do some work externally. We have to apply some force externally. That force is called here F external. Don't get any confusion between this one and this one. F suffix ele means this electric field, and this is the external force, and this is electric field. This is a repulsive force, and this direction, this one repelling this one. But my intention is to bring this Q from R to P. So for this, I have to apply external force in this direction. In this direction, then only it comes. Okay, direction is fixed. Okay, how much of magnitude we have to apply? So suppose if it is repelling 10 newtons, and we have to apply minimum 10 newtons of force, minimum 10 newtons of the force. And if you apply less than 10 newtons of the force, and this charge, this test charge will move like this only, away from Q. But my intention is to bring from R to P, so that is why we have to apply a minimum force 10 newtons. More than force, okay, well and good, it goes minimum force. So here F external, it should be equal to F external. The relation between these two, ELE, the magnitude is same, but the direction is opposite. That is represented here by the negative sign. Okay, right. Now you are able to see, I think so. F external is equal to minus F LE. This is the electrostatic force, and this is the external force. Okay, and we know the formula for F electrostatic force. By using Coulomb's law, we can say K into capital Q into Q by this distance. Let us call this as the R square. R square. And this much of minimum force we have to apply. Okay, this is the electrostatic force. And here R means from here to here. This is okay, from here to here. This is R square. Now this is when and here the important bits are when the charge was moving from R to P here. What is the acceleration? What is the acceleration on this just a charge? Can you guess, anybody? And this acceleration is 0. Okay, you may ask me why it's 0, and why? Because of the net force is 0. How can you say net force is 0? Electrostatic force and external force both are having same magnitude but opposite direction, hence they will cancel. So the net force F net is equal to 0. F net is nothing but ma. Acceleration A is equal to 0. So here the important, when the test charge was moving from Q to, I mean R to P, the acceleration is 0, and in the force free field it was moving. Note that up to this one, everything is clear to you, I think so. So now we are doing work. This external force we are applying against to the electrostatic field. Okay, so here I am going to define potential difference between 2 points. The definition is, it is potential difference is represented by delta V. How it will be defined? The amount of work done per unit charge, or here test charge. The amount of work done per unit charge to move between 2 points, that is from R to P. How we are doing work against the electrostatic force? Against the electrostatic force. So this is, and here this is F external is the what is that called, variable force, not a constant force. We know that work done by variable force, the formula it is W is equal to integral F into ds, F into ds, and this is F external into ds, or we can write down F, sorry, integral, in the place of F external we write down minus F electrostatics into ds. Where, what do you mean by ds here? Ds is the small elemental length, ds, small elemental length, this is ds, and here this is. So here we can find out. Okay, this is the formula for work done. And what I am saying, this is the amount of work done per unit charge. To move this charge here, we need to do work from R to P. That amount of work done is W. Let us say 10 joules. W by Q. W by Q. And if this P is more distance from R to P here, we need to do more work. We need to do more work. Okay. So here delta V is equal to what we can write down, W by Q, the amount of work done per unit charge to move between 2 points against the electrostatic force. That is called potential difference between P and R. So here the units for potential difference, it is 1 joule by 1 coulomb. 1 joule by 1 coulomb, and this is called here as the 1 volt. 1 volt. Okay, this is basically about potential difference between 2 points. This is a definition, here it is. I think so all of you, it is very clear to you. So first of all, we'll concentrate only on the electrostatic potential, and subsequently we'll go to capacitance. Okay, and next one, we'll define electric potential. Now up to now I defined potential difference, and now we are going to learn electric potential. So if you understand electric potential difference, you can easily understand what you mean by electric potential. So this is nothing but, here also you can say the same thing, plus Q is capital Q, sorry. This is electrostatic force. And to define electric potential at a particular point, so here I would like to find out how much of potential is there. So here how much of electric potential is there. So what we need to do, and we have to keep this test charge at infinity. That means this R should be at infinity. This R should be at infinity. So not here. This is R. And this is infinite point. Electric field is equal to 0. No matter, here it is. This is infinite point. Infinite point. So from here, this is the test charge. So here, from here, to move this test charge, we have to apply the force externally like this. So the amount of work done. So for this one here I am writing the definition. It is electric potential. Electric potential is different from potential difference. Okay, Electric potential, this is at a point here, at a point P. So how to find out electric potential at a point P? Simply the amount of work done in bringing a test charge from infinity point to this point. Suppose if you have done work 10 joules to move the charge from here to here, 10 joules by Q. That is called electric potential at this point. And suppose to move this point, we have to do more work. So here more potential will be there. So to bring here from here to here, we have to do less work only. So lower potential will be there here. So P, and let us say this is S and this is A. So at which point the potential is more? A, P and S. Here we have given 3 points, and at which point the potential is more? Obviously at S. Why? We have to do more work to bring this charge from here to here. Why? Because of when we are bringing here, it is more displacement is there. Okay, so we have to apply more force, more external force, more repulsive force will be there. So to overcome that, we have to apply more amount of the force. So this may be simple basic questions, conceptual questions they may ask. So here electric potential at a point and electric potential difference between points, between 2 points. Okay, so electric potential means, here I am writing the amount of work done per unit charge to move it from infinity to a point in a electric field against electric force is called as electric potential at that point. So if you want to find out potential difference between 2 points, between this point and this point, simply we have to move a test charge from here to here, from A to B. So how much of work is done on that charge, and that resembles electric potential difference. Suppose electric potential only you have to find out. So bring a charge from infinity to this point, that amount of work done per unit charge. So here for electric potential difference and electric potential, both are having same units. This is work done per unit charge, 1 joule by 1 coulomb, and this is called as the 1 volt. Simply this is the volt. Okay, and whereas electric potential is a scalar quantity, potential difference is a vector quantity. This is the difference, it is scalar quantity and this is the vector quantity, whereas for these both the units are same. So with this I am stopping this one. This is a little bit introduction about the second chapter, and the next class I'll give you some more teaching, some more advanced teaching on this electrostatic potential. Thank you so much, happy learning.